Hello, everyone again. So this is a bit more specific story about one component of the satellite laser ranging system. Just a brief reminder that the satellite laser ranging is one of the space geodesy techniques which measures the distances to the satellites with extremely high accuracy. We are talking about single shot precision below 1 centimeter, and as a result, we can obtain the coordinates up to the 1 millimeter on the ground. This is not used only for the space geodesy, but also to support space missions. Some fundamental physics, as an example, is the so-called GREAT experiment, which recently verified the Einstein's general relativity, the gravitational redshift. We also took part in this experiment to measuring the distances to the two dysfunctional Galileo satellites, which were in elliptical orbits. And all this method relies on very accurate time measurements. And another advantage just is that we are measuring this distance with an etalon, 1 meter by definition. So this is gives a laser ranging as a unique method to determine where the geocenter of Earth is. If you know a little bit of the science history and geodesy, that determining the Earth's form where parameters was a really great, an expensive venture. Just to remind that the first definition of meter was done in the French Academy of Sciences, and it took 7 years to define the meter which we use today. It's already defined. So, and this system relies that there is interplay between the tracking system, which ensures that we can track the satellite and transmit and receive pulses, and from the measurement system, which consists from the laser, for detector, and very precise event tagging, I would say, or time interval measurement. Here we will talk about one type of detectors which we recently used. Try to use. I think moving forward. Oops. So here is a brief summary of motivation. It is some state of art, what is used, and because it's quite expensive venture, also if we find that something works, usually not a lot of motivation to try other things. So the currently dominating technique for detectors are so-called single photon avalanche diodes and PMT or photomultiplier tubes, which is now taken mostly we are one of the few who are still using them. There is other options like a multi-channel plates, some exotic more detectors, which I will mention later. And also, it's not so we just pick one detector. There is, for each detector, we have each pros and cons. What we are looking for is the fast rising times, about active area, because we have to track, and focusing on very small areas is tricky in the telescope, and high quantum efficiency and low dark noise. And therefore, each of the detector types has its own advantages and disadvantages, and also the cost. And for one experiment, particularly for the space debris, we looked for something which we can afford within frame of the project, and which was high quantum efficiency, a sufficiently large area. And then we run into, let's say, a bit obscure type of detector. So here is a brief summary about detector. All these numbers are indicative. There is, for each parameter, there is a range. For the classical PMT, okay, this is quantum efficiency is upper, and some typical surface areas. You can find a lot of variations for each. And here's the full range: avalanche diodes, multi-channel PMTs, and HPDs, and also so-called nanowires at the end. And for in telescopes, in optical systems in general, which are used in laser ranging, it's very hard to achieve the stable focusing on everything which is less than hundreds of microns. this is a bit limited. There is some successful experiments also with these nanowires because they have virtually no noise, but to maintain also the cooling and focusing is a really tricky part. And also the price. For example, some state-of-art multi-channel PMT from Hamamatsu, we get a quote, 75K, lead time 6 months. So it's a bit, let's say, it's out of reach for us. And it turns out that so-called hybrid photodetector could be a very interesting alternative. It was quite a hot topic about a decade ago in the nuclear instrumentation, but then somehow is not mentioned very often. We just know that it's also used in confocal microscopy and some other fields. So what it is here is from Hamamatsu handbook. I think that Hamamatsu is the only company which produces this type of detector. In the left side, this is classical PMT. On the right side, this is hybrid photodetector. So it is basically just a photocathode, but with a very high potential difference. We are focusing on the semiconductor detector, and in this way we can, let's say, produce very well-defined single electron response. It has a sufficiently large area, and yeah, and not the least, it's also we can afford it. And so we try to take a closer look on this type of detector. So we are just rebuild our telescope receiver unit to install the alternative detector. So we are still using as a primary detector our PMT, and for space debris, and maybe for some other purposes, we will try to use this HPD photodetector. So here is during the assembly, it is already outside, so it's on field work. It's not yet fully assembled, but just gives us some idea how this detector unit looks like. On the left bottom corner, this is connection to the telescope, this main optical path, and you see both detectors which you can switch easily between them as a PMT or HPD. So this is a closer look on HPD. How the package looks like. We bought it from German companies. This is available as a fully sealed package, including the preamplifier, cooling, and protection shutters, because this time we are using the model 40, which is the highest quantum efficiency at our laser wavelengths, 532 nanometers. But it also has this arsenide photocathode, which is quite sensitive to light, and so should be protected. So here how it looks like the single photon response. On the left side is the manufacturer. This is very first thing which we did, just to take a look. Is it so? And yes, this is a well-defined signal. And here comes one advantage of this hybrid photodetector, because there is only one amplification stage, there is less variation. And so we can very clean, let's say, separation between single photon and few photons. In multi-photon mode, it becomes more tricky, but nevertheless, this is one of the advantages of this type of detector. And here, one of the things is in laser ranging, because we are talking about centimeter and millimeter accuracy. If we convert it to time, we go down to the picoseconds. And there is two strategies. One is try to stay when tracking in single photon mode. So we have, let's say, uniform type of impulses, and if we measure the distances, then it's this variation of this so-called time walk is minimized. Another strategy is to build the compensation mechanics, and it can be done either in hardware or software. One very popular way is the so-called constant fraction discriminators. We also have used it, but we are mostly using digital compensation. So we build a compensation function which we apply to the measurements, but it requires also for us to measure the signal strength. To record in parallel. And here on this chart is a kind of on the x-axis is signal strength in relative units. It is actually expressed in nanoseconds. because it's amplitude to time converter, but it's approximately, it's very close to millivolts, but not exactly. On the upper is just a distance in picoseconds. And this operational part we indicated by red arrows indicates in which, let's say, range we can safely compensate. Oops. Yep. So here is how this compensation curve looks like for the HPD, and similar for this Hammermatz. We are now also researching the time wall characteristics of both, how to best fit this and to compensate the amplitude. And here are some results. For example, this is using so-called standard calibration procedure. So we are in this case we are using optical fiber as a, let's say, to measure the distance. And I would say there is one thing is we are currently using the 2 generations old event timer with amplitude measurement, and which lives its last days, and its performance is, let's say, much worse than specified. So this number is a little bit higher than it should be. I think with this existing setup, we can go even with the PMT to the, let's say, 5 millimeters or so. Oops. Okay, here the HPD, it's slightly less, but as I said, this is not indicative. We are now waiting for the new event timer. A presentation about this will be in this afternoon from the Institute of Electronics and Computer Science. We are developing together a new timer, which will have as a RMS about 2 picoseconds, 2.5 to be precise. Our existing, the max best value is about 8 picoseconds RMS, but actually I think is more lower, and it's not well stable as well at the moment. And so here is a brief summary of this data. So the results are encouraging. We have tested also with the satellites. Here is typical, let's say, satellite past LARES-2, which is a geodetic satellite quite far away. So we get about RMS about 16 millimeters single shot, but this is, as I said, should be around 1 centimeter. It's due to the old event timer. And the same path we took with HPD, we already get an improvement. We expect that this HPD, we may use it and get even accuracies which is comparable to the best stations in the world using SPAD.
Just for colleagues far away, which means
this is okay. This is more about altitude about 6,000 kilometers or more. I don't have this number in my head. I know the Lagios is 6,000. LARES was launched just this summer, and this now and altitude is not yet set in my mind. So for other satellites, I already know it. Okay, this 6,000 kilometers closest distance. This is. And this is a small cannonball satellite. So, okay, here is some references, and to summarize, so what we have discovered, because we are first in the world who are trying this type of detector for laser ranging. It looks promising. We are preparing the publication on it. The disadvantage is daylight ranging, because satellite laser ranging can be done only in the daylight. And then we get a pretty high background noise from the sky. And with a reduced field of view, we can get more megahertz in the. And for this type of detectors, we should be very careful because it shortens their lifespan. If you use this, so this is kind of. From other hand, there is other types of these hybrid detectors which has a different photocathodes, and maybe it's safer. And for, let's say, classical laser ranging, which are retroreflectors, we don't need this top quantum efficiency. We can live also with 10%. And to keep this type for the space debris, we hope to do the experiments this summer also with the space debris tracking, including in bistatic, and also with our laser we will try. And so see what we will get. So as this is kind of work in progress, so probably one of the second time we are mentioning this is some kind of meetings or conferences. The first time we mentioned it was in ILRS conference in Spain last year, in the end of the last year. So thank you, that's for your attention, that's it. And the final picture is how it looks like.
Okay, now questions, please.
Maybe this question is not directly connected with the topic of your presentation, but just maybe like a question from common physics. Is it possible to absorb like effect of Doppler effect from reflected satellite when you shooting in front or shooting in back?
Well, we are using pulsed lasers. It should be possible with continuous laser. Actually, such ideas was present in problem is energy. For these pulse lasers, we don't have sufficient energy to make the spectroscopic measurements because we are getting back from 1 to about maximum hundreds of photons. Yeah, for per return. And we are also trying to be, as you see, this time wall compensation is try to stay in the 1 photon, 2 photons, 10 of some photons, just to be able to get the accurate range measurement. But such ideas are alive, and there is some high energy laser systems which will try to utilize also the specially assembled pulses to try to get also the Doppler shifts. And I know at least 2 experiments. One is by Lockheed, and another one is a GPL, so-called tabletop observatory in California, which will try to use the continuous wave laser also for satellite tracking.
Okay, please,
you have quite low powers. We understand that. How is the general situation, say, in satellite ranging and also, of course, in laser guide star type of thing? You need to be in contact with a local air tower when you operate, or how?
Yes, this is we have contacted our local air tower. We also have the ADCB receivers. This will give indication about planes. We have a visual safety measurement. Yeah? Yes, that's true. And also we are, because our transmitted beam is quite wide, we are about 1 meter. So the energy density is already, when exciting, is lower. Yeah, we are not strictly eye safe at the vicinity of the laser. Yeah, but at the planes, I think we are also on the safe side. And actually, okay, this is to hit the plane is really a hard task.
Well, even harder to hit the satellite.
Even if you try to special, yeah.
No, it's always an issue in laser radar. Of course, I worked for 40 years in this area, so it's a question of, you know,
yeah,
judgment you can have and so on. I mean, with the laser guide stars, I think it's a completely different game, of course, because it's high power. And,
yeah. This is same for this high power lasers, which I mentioned, this tabletop and some others. Yeah. And this is also one of the reasons so-called bistatic or multistatic ranging, when you operate a few high energy lasers, yeah, and try to pick up the scattered photons from multiple places. Because to install in each place high energy laser is really, it's a tricky thing also to manage.
Okay. Please.
It's not a question, just a little bit comment. I am not in field, but I'm really impressed by what colleagues are doing. Latvia now is becoming Space Surveillance Program participant and official participant. It's a lot of safety reasons for us as such. And there's also a challenge to laser ranging for nanosats. Many of them will be commercial. Possibly there is some commercial outcome sooner or later, because they all need, most of them need some ranging to knowing where they are and what they are doing, as well as contribute to European Green Deal. it's also not evident, but it's really this network of satellite ranging across the world. They are main contributors to this data that we can say that sea level is rising by 3 millimeters. Always you're wondering how you can measure when waves are. They are collecting this integrated knowledge and so on and such ways are contributing. And I to our council, still as a chairman, if suddenly Riga out from this game, it was absolutely society worldwide was very strong team members, really strong team members.
Just about this sea level rise, I would a bit clarify. We are calibrating the laser altimeters. So that because laser altimeters, which works in satellites, relies on this precise orbits, and this is one way to verify it. But with satellite laser range, so we know our target list, we have all these oceanographic satellites. This topics Poseidon mentioned in the presentation by Ilma, which is no space debris. It also is one of these type of satellites. Now it's a JSON 2, JSON 3, and Cryosat. But really, we need decades of measurement to say definitely what's going on. So this is a bit premature to say that everything is rising. We don't know. This is interesting.
Okay. Nobody. Okay, now we go on.